So very good evening to one and all. So welcome to our 30-day masterclass on advanced VLSI design and verification. So very good evening to one and all. Thank you for your presence. Mohammed Tawfiq, very good evening. You joined early today. So Sri Satya, very good evening. So and then today we are gonna see RAM. So we are gonna design the RAM, simple single port RAM. So we are going to write the Verilog system Verilog code, and then we will write the test bench code for RAM protocol RAM. So thank you for response, your Tawfiq. So let's wait for a few minutes, then we will start the session. So Venkata, very good evening. Muhammad Tawfiq, Sri Satya, Sri Krishna, very good evening. Sri Krishnan, Krishma, very good evening. So thank you for all your daily presence in our master class, and also yearly comer. So RAM is very important kind of memory in our day-to life or day-to electronics life. Why? Because of without RAM there is no happening in electronics. So we need RAM are mostly for speed execution of instructions. Okay, RAM is mostly important. So and then Wilson Paul, very good evening. Sweta, very good evening. So Sankar Reddy, very good evening. So thank you for your presence. So today we are going to see RAM and then FIFO memory, FIFO buffer. So how the FIFO works, how we are design the FIFO buffer. Why? Because of FIFO, like a first in first out, is kind of memory. It's like kind of buffer. It's very important. Why? Because of so while writing the Verilog code, we have to make synchronization between the one block to another block. So on the time we can use the FIFO buffer to make synchronization. So synchronization is nothing but, so if you having the two blocks, like assume like you having the controller, you having the one slave device, both are works in different clock frequency. So there is a chance to getting the error, okay, data loss or bugs. So if you want to make the both devices like a master or controller devices or slave devices, you want to make us work together, so with like a synchronized together. So how we can make means by using this FIFO kind of buffer we can make that. So I will show you in this session how the FIFO buffer is using for synchronization. So thank you guys, thank you for your presence in our 30-day masterclass. Today we are going to see RAM and FIFO. So let's wait for a few minutes, so and then we will start. So we are going to see the RTL, like a Verilog, system Verilog code for single port RAM and then test bench also. So and then we will see and then we are going to see FIFO buffer. So let's wait for a few minutes, like 2 minutes. We will start at sharp 5, sound 5. So can you respond in chat box how many people are aware of the memory type? So what are the types of memory? If you know the answer means just put the types, how many types in chat box. So good evening, better thoughts, good evening. Sampath, good evening. So can you just respond in chat box how many types of memory we have? So what is the nature of the memory? Can anyone if you know means you can respond in chat box. So how many types of memory we have? So and then what is the memory nature? So nature means it if the memory is stored permanently or temporary, means what we are calling that. Okay, RAM and ROM. Okay, so RAM is permanent memory or temporary memory? Is RAM is permanent memory or temporary memory? RAM, ROM, cache. Okay, flash memory. So there are a lot of memories we are using. So EPROM, and then cache memory, flash memory, and then DDR, DDR3, the DDR, DDR2, DDR1, DDR3. This all comes under the RAM only. SDRAM, DRAM. So memory storage device types RAM and ROM. So volatile and non-volatile memories. So RAM is volatile or non-volatile? So RAM is RAM is volatile or non-volatile. So how many people are aware of the volatile and non-volatile? What is difference between the volatile and non-volatile? So volatile memory, so RAM is comes under the volatile memory. It will store the data temporarily only. Okay. So yeah, correctly. Sri Satya were telling exact answer. Volatile memory. So RAM is volatile memory. It will store the data temporarily. Okay. ROM is permanent memory. It's a non-volatile in nature. Non-volatile memory. It will store the data permanently. So EEPROM, ROM, and then flash memory. These all store the data permanently. Okay. So and then coming to the flash memory, permanent memory. So coming to the RAM, so temporary memory. So why we need for temporary memory? So can anyone response in chat box? Erase after erase after device switched off. Yeah, it is a temporary memory. When power of data also related is a temporary memory. So why we need temporary memory? So why we need temporary memory means, so we know that in the second day of class we see like a computer architecture. So the computer architecture will execute the instructions, addition, multiplication. Okay, so that registers are store the data temporarily only. So temporarily only. Okay, the for example mul opcode 1 and then 2 registers. So the instructions that are stored in temporary memory only. So if you store the permanent only means it will take more time. Why? Because of writing, like a writing into like a non-volatile memories take more time. So if you want to store some particular data into non-volatile memory means it will take more time to write into the non-volatile memory. But in the volatile memory we can fastly write the data into volatile memory. Okay, so that is difference. So this is the main equation. Main thing is, so the execution instructions are stored in RAM memory. So then only that ALU or control unit will fetch the data from RAM, like a temporary memory, then execute. So we can easily write we can easily overwrite the RAM memory. Okay, but you can't overwrite the ROM. So by using the EEPROM, electrically erasable programmable readable memory, you can also overwrite the ROM, but it will take more time. So yeah, to access the data faster. So this is the main purpose of RAM, to access the data very faster compared to the ROM. This is how we need RAM. Okay, this is why we need RAM. Okay. So how many people are written? How many people are know the single port RAM? So what is my single port RAM? So Chaudhary, very good evening. So Manmeet, Lamba, one read and then right head is read in non-volatile memory. Okay. So very good evening, Narayanamurthy. better thoughts, better thoughts. Very good evening. So we'll start the session. So we'll see there's some basic definition of RAM. So I hope you guys understand the RAM functionalities, usages. So we'll see some basic definitions. So random access memory. So it's type of computer memory that store data temporarily. We know that. So when you turn off your computer, the data in the RAM disappears. We know that. So unlike the data on your hard drive, which stays saved. Okay, so without RAM the computer won't start. So you can see here this picture. I'm telling like a RAM is essential for starting the Windows. So and then without RAM the system can't start, just like a car without just like a car without fuel. So why in this picture they are telling like a RAM is essential and then starting for Windows? So why? Because of the RAM. So we know that if you want to boot the OS, like a Windows OS, means you need bootloader. Okay, bootloader is like a BIOS, BIOS, and then it depends on bootloader. So some laptop companies will use a different bootloaders. So mostly Intel kind of thing, it will use a BIOS bootloader. Okay, in that BIOS bootloader, what we are having, so we are in that BIOS bootloader, it having only the instructions. Okay, instruction of boot loading. So that instruction are stored in EEPROM. So EEPROM means nothing but electrically erasable, programmable, read-only memory. That instructions are stored in EEPROM. So okay, so we have the instruction, we have the boot instruction in the EEPROM, in the read-only non-volatile memory. But how it is executed? So for to execute this, so it need one input signal from the device. That signal is clock pulses. From one clock cycle, if it is that particular EEPROM, that particular BIOS, it receives a one clock cycle from crystal, means it will execute the first instruction. So the particular first bootloader instruction, it having the it will call the lot of instructions in the Windows OS. So lot of sub instructions we have. So if the PPROM, it having lot of instruction for the boot loading, for loading the Windows OS. So it having one instruction under under that particular one instruction, it may be having some lot of instruction, sub instruction. So that instruction are created and stored in the RAM memory. So our OS will our control unit will fetch the instruction from the RAM, and then it will execute in the control unit and then arithmetic logic unit, and then you will and then if the flow is happening, means based on this flow only our Windows OS is booting. So it's like we are using Windows OS. So firstly we have clock frequency, clock input from crystal. We have to give to the EEPROM having the, it's like a bootloader, it having the some instruction, bootloader instruction. So it will execute one by one instruction. While executing the one by one instruction from the bootloader, it will create another instruction for OS. So that instructions are stored in RAM memory. So it is a temporary memory. Why? Because of every time I'm calling the instruction in the EEPROM, it will create other instruction to boot the OS, means we have to store in the temporary memory. Then only the CPU will get the instruction very fastly from the RAM. Okay, and then OS will boot finally. So this is how our Windows is working. So our Windows will booting. So this is a process of Windows, like any OS, Windows, Linux, Ubuntu, any OS are booting. Okay, this is how it booting. So this is a purpose of RAM, to store the instruction, helpful for the CPU faster execution. Okay, this is the main thing of so we can store the main instruction in the EEPROM, but some instruction we need very fastly, then only we can do the fast computation, we can do the quick boot loading. So for that reason we have to use RAM only. Okay, so if you want to learn more about this RAM thing, means you can join our YouTube channel. So we are going to post the in-depth knowledge of RAM, like a circuit diagram, like a transistor circuit. So what is the difference between the CMOS transistor circuit for RAM and ROM? So we are planning to post the video on YouTube, so you can subscribe for more kind of knowledge. Okay, so and then this is a simple block diagram for the single port RAM. So you assume like it's a single port RAM. Sorry, here I just made mistake of ROM. Assume like it's a RAM. So RAM means kind of memory. Okay, RAM is kind of memory. So RAM means we can store some data in the address memory, in the memory locations. From like you having one memory, means it having a lot of memory locations, you can store into the memory location, and then you can access the memory location by using the address. So without address you can't access the memories, you can't access the RAM. So how you can access the RAM means by using the address, clock input, and then enable signal. So this is a main input signal for the RAM, and then output signal is DOUT. So you can see here input signals like this is my RAM. So assume like it having some memory locations. Okay, So if you want to store the particular value in my second memory location, means you need the second memory location address, and then you need the data d in, and then you need the clock pulses. So it is also based on the clock only, based on the each passage of clock only it will work, RAM will work, and then D out. So this is a simple block diagram of the RAM. So D in, D out, clock, enable. Right, enable is used for saying so whether I can write into RAM or whether I can read from the RAM. So the enable signal will helpful. If it is enable signal is high, means like a write enable is high, means if this particular signal is high, means like a enable equal to 1, means I can write into RAM. So if it is low, means I can read from the ROM. So okay, I can read from the RAM. So RAM is one memory, we can read and we can write, and then this is the main purpose. So we can read and write means how we can read and write by using the address. We can read from the particular address, and then by using the address we can write to particular address. This is how RAM will works. So and then before going to the start with code, I will tell about internship program. So if you guys are really interested, you can join our internship program, 1 month of internship on advanced VLSI design and verification. So these are the benefits you will get. So you will get the all 30 days recording session, all PPTs, and then you can also download the source code. So and then you will get the exclusive 4 projects. So and then you will get the internship confirmation letter from IETE, and then you will get the 6 months of LMS success of recorded sessions. So and then you will get the weekly live sessions, and then we are providing the task also. So and then in the 7th benefit is you will get the internship academic internship report. If you are studying in college, means it is useful for you. So and then finally you will get the internship certificate from IETE at the end of the 1 month. Okay, these are the benefits you will get from internship program. So our regular fee is 4,999. In this masterclass period, we are provided a discounted fee of just 999. So by using this registration link, also you will get the link in chat box, so to get the internship program. So in this limited time period offer, so you will see after clicking that link, you will see this window, and then here you have to choose advanced VLSI design and verification. Okay, so and then this is a sample certificate you will get at the end of the internship program. So this is from the IETE. So this is a certificate look like of internship program. So and then we'll start the coding part. So okay, already I written the code, sample code, or else I will show you in the here. Okay, so this is a main code of design code, only 41 lines. So this is a main design code of my single port RAM. So single port RAM, so we know for single port RAM we need the signals, input signals like a clock, reset, enable signal, and then data in. So these inputs, and then data out is a output, only one output, and then 4 inputs: clock, reset, enable signal, and then data in. Okay, so for creating the RAM in the Verilog code, we need the input and output signal, and then we have to make sure how many memory location it having, so size of the RAM. So I am using one parameter here, data parameter, like a data underscore width, address underscore width, and then memory underscore depth. So depth means it having the 16 memory location. So and then data width is 8-bit. So it means, so in my RAM, assume like it's a small kind of single RAM, it having a 16 memory location. Each and every memory location I can store 8-bit of data. Okay, so totally 16 into 8 means you will store that much of data in the RAM. So I'm going to create that RAM only 16 memory location. From one memory, for each and every memory location I can store 8-bit of data. So this is a data width. Address width is also 4. So why I am using the address width means, so there are 16 memory location. To point the memory location means we need address. So by using the 4-bit of address, I can point the 16 memory locations. Okay, 44000 for first memory location, 0001 for second memory location address. I am saying the address. 0010 is a third memory location address. So okay, so address width is 4, data width is 8, and then memory depth is 16. So this is my parameter. Okay, this is my input and output signal. You can see here clock, reset, write enable. These are my main inputs. Clock, reset, active low, reset, and then write enable. So it means if this particular write enable signal is high means it can write into memory. It can write. So and then if it is low means this particular signal is low means it can read from the memory. Okay, can read from the memory. So and then data in. So you can see here data underscore width. It means 8 bit. So I can store 8 bit of data in each and every memory location, and then data out. So I will get the 8 bit of data only from the output. Okay, only one output, 4 inputs. So this is the memory array declaration or memory creation. So I am using the logic data type. So you can see here data underscore -1. So data with underscore minus, data with having the 8 bit. So 7, 8 minus 1 7 down to 0. It means 8 bit. So and then this is my memory name, memory. So and then 0 down to memory depth -1. Memory depth is 16, -1 15. It means -1 15. So 0 down to 15. It means 0 1 2 3 4 5 up to 15. So 16 memory location. Each and memory location I can store 8 bit of data. This is a memory creation. Memory creation. It is very simple code. This is how the RAM. This is a basic simple code of RAM. So like if you assume like a 8 GB RAM, 16 GB RAM, they are also having this kind of signal only, read and write signal, enable signal, data in, data out, and then clock reset only. But for the speed communication they will use some protocols inside the RAM. Okay, so and then this is my memory creation, like a RAM memory creation. So this is my whole logic. This is very simple logic only. The main thing is if my write enable is high means I can write into memory. If write enable is low means I can read from the memory. This is a basic logic. Okay, so I'm going to use always passage of clock or negate of clock, negate of reset. Why? Because of I'm having the active low reset. Active low reset means if the reset pin is low, having the low value means it is defines my RAM in the reset condition. If the reset pin having the high value means the RAM will work means it can read or write. Okay, so if a reset having the low, like a 0, okay, reset underscore n is a signal. If it is having a 0 means it indicates that it is telling us your RAM in the reset condition, it won't read and write in the reset condition. So this is a reset condition. Okay, so if it is reset is high means, so I am storing the 0 value. So you can see here I am using the one for loop. So BIOS bootloader is used to dual boot, like install on multiple OS for different purpose or lot of underscore. Yeah, Muhammad Tawfiq, you are correctly. So BIOS is like a bootloader. So you can boot Ubuntu, and then you can boot Windows OS from the BIOS bootloader only. Okay, if you having the two OS means it will ask whether which OS I have to boot, like a Ubuntu OS or Windows 10 or Windows 11 OS. You can choose from the buttons. So basically it having some instruction to boot the OS. Okay, in the EEPROM. So why we are storing the EEPROM means electrically erasable programmable read only memory means, so it is a permanent memory. So we know that it is a permanent memory. So the main instruction, like a bootloader instruction, like a booting kind of things, must be stored in the permanent memory only. Okay, why? Because of it is we won't erase. So every time we switch on the computer means it will execute. That's why we are stored that instruction inside our EEPROM. Okay, so this is my reset condition. I think thank you for response, Muhammad Tawfiq. So and then just a minute. So Jack's very good evening. So and then this is my reset condition. If my reset my reset signal is low means I am saying that I am storing the zero value in my memory. Why? Because of I am using the active low reset. There is a two thing like a active low, active high. So active low operation, active high operation. So active low means if it is in the active low means it will execute that kind of things. So I am using the active low reset. So if a reset signal having low means like a zero value means it will stay in the reset condition. My reset condition is nothing but I am storing the zero value each and every memory location. By using this for loop, I am incrementing the memory depth like a 0, 1, 2, 3. I'm incrementing one by one. So at every incrementing, I am storing the zero value. You can see here zero value to my memory. Okay. So here I will always incrementing. It will do iteration. It will start from 0, 1, 2, 3. It will go up to memory depth. Depth means 16. Okay. So firstly memory is a array of 0th location I am storing 0, array of 1 I am storing 0, I'm storing 0, and then array of 2 I am storing 0. This is how it works. Okay, I am storing the 0 value on each and every memory location in the reset condition. And also data out, like my output signal also will give the output as 0 at my reset condition. So if it is if else statements, if it is not in reset condition means I am giving like I'm checking my write enable signal. So write enable is nothing but WE is nothing but write enable. If it is high means I can write into memory. So if it is having high equal to 1 means if it is having high value means I can write into memory. You can see here my data, this is my DN input signal, input value. I'm directly assigning to my memory. So how I am assigning the memory means based on the address. Based on the address value I am assigning to my memory location. And also I am assigning directly to my output. Why? Because of they both are works together in the single clock cycle. Why? Because of this is a non-blocking assignments. So in the it will do parallel execution. So if you want to use this means you will get the output in the next clock cycle. So in the first cycle I am storing into memory, but it will reflect to me in the simulation in the next cycle. Okay, that's why I'm using the write throw behavior. And then this is my, if it's write enable is low, if write enable is low means I can do the read operation from the address. So this is the address from the memory address, depends on address. I am assigning to my output signal. So output signal is nothing but D out. Okay, so if the memory of 5 means the memory of 5 address having 5 means, so in the fifth memory address what the value stored, so that value will directly assigning to my output signal D out, D underscore out. So this is a simple RAM code. It is very simple only. I hope you guys are clearly understand this code. It is very simple only. Write enable is high means I am writing into memory. If it is low means, if it is low, else condition will execute it. It means from the memory I am assigning to my output pin. Okay, output signal. So this is the so this is a basic simple RAM code, single port RAM. So why it call as single port means, so it can do only read and write from the it can do only read or write at a time. So why? Because of it having the only one enable signal. So double port RAM means, dual port RAM means it can do read and write on the same time. So that's why it's known as single port RAM. We can only read or write at the same time. You can't do both at the same time. So you can only do one thing in the one clock cycle, one passage. And then we're gonna see the RAM test bench. So this is a RAM test bench. So here also I'm declared the like a parameters like a data width, address width, memory depth, and then clock period. So this is, so I'm going to use this parameter for creating the clock pulses, and 10 nanosecond means 100 megahertz. Okay, so the whole time, so taking the clock period is not how we can say. So the one cycle of clock, the time taken of one cycle is 10 nanosecond is that clock pulse is 100 megahertz. So if it is having 20 nanosecond for one cycle, like one passage to another passage, that's the time taken. If it is a 20 nanosecond means the clock frequency is 50 nanoseconds, sorry 50 megahertz. If the time taken of one passage to another passage is 10 nanosecond means that clock frequency is 100 megahertz. So there is some calculation, I already said no. If you follow that calculation means you can easily find the frequency based on the time. So and also you can get the time based on your frequency, time taken of the clock cycle. Okay. So and then this is my test variables. This is my internal signals for my test bench. So here I am doing instantiation. This is my design code, module name, single underscore port underscore RAM. So I am doing instantiation with my test bench. Then only I can pass a stimulus from test bench to design code. So okay, and then this is a clock generation. You can also use forever keyword to create the clock. So previously we are using the always block to create the clock pulses, but here you can see here this is my initial beacon simulation block. Initially clock having 0, and then forever it will do like a same, it will works like a always block, but the main difference is you can't use always block inside the can't use always keyword inside your initial beacon. Okay, inside your initial beacon. So you can't use the initial you can't use always keyword inside your initial beacon. You can use only forever block. Okay, so forever at every 5 nanoseconds, so 10 by 2 means 5. At every 5 nanosecond I am toggling my clock. Okay, so and then this is my main stimulation time. So reset low, it means I am in the reset condition, and that time write enable is low, address also 0, data in also 0, and then single, this is my display statements to see output in my transcript. Single port RAM test bench started. Okay, and then so test this is my display statement for my test 1. So clock period, I'm waiting for clock period. This like a clock period is 20 like a 10 into 2 means 20. After 20 nanoseconds I'm just off my reset condition. How we can off my reset condition means giving 1 for reset pin. Okay, if it is having 1 means it will do execute, it will do perform the RAM operation. So after the 10 nanosecond I'm doing this like a dollar display test 2 basic write operation. So this is a basic read and write operation. You can see here inside my for loop I'm calling the two tasks like a write data, read and check data. This is my task. Okay, this is my task. So where the task means, you can see here there is my write underscore data task name. This is my task. Here I'm doing like a writing the data into my RAM, into my memory. So how this task having the input and output signals, address like a write address, write data. So I'm going to I'm just directly assigning the write underscore address. This is my internal signal. I am assigning into my main signal. So and then here I am having the write underscore data. This is my internal signal. I am assigning into my main signal. So and then write enable low. It means I can read from the memory. After the one cycle, I can read from the memory. Okay, return. So I am displaying the return address data. Okay, this is how I'm displaying the what I am writing into memory, and then what I am read from the memory. Okay, so and then read and check. So this is a read and check. It having the input and output signals for the task. So here write enable is low. It means W is low means I can read from the data. So read address I'm assigning to my address. So from this address I can read from the memory. Okay, so after the one passage I'm increasing my test count. The test count is an internal signal, it will do increase my test count. Okay, so and then data out, so output of RAM and then expected. So if it's both are same means both are same means the RAM core will work fine. So if both are different means there is an error. Okay, there is an error, so this means error count will increase. So and then this is my main initial monitor. It will get the all the it will capture the all the changes and then it will display. So and then this is for displaying the waveform. So and then I'm going to the test cases. This is my first test case, and then this is my second test case, basic read and write operation. This is my third test, write all memory locations. So how we are going to write all memory location means, I am here, you can see here I am calling this task, I am calling the task in my for loop, and then while calling my task I am passing the arguments. So I, and then data, this is my address, I is my address. So why? Because of for loop will always do iteration. When it will start from 0 and then 1 2 3, it will do iteration. It will start from 0, so 0th location, and then I into 16 plus 1, it means 0 into 16, 0 into 16, 0 only, and then plus 5, 5. So in the 0th memory location I'm storing the data of 5. So I'm calling the write data task, write underscore data task. So this is the task, it will do the write operation. Okay, so and then this is my test case 4, read all memory location. So by using the for loop I am reading from all the memory location. So and then this is my random access pattern. So you can see here address, I am assigning the random $random. It will do the random, it will give the random random values for this signal and also random values for the data in. So I'm calling the data, write data, and then read and check task to display my outputs. This is my test case 5, and then this is my test case 6. Here I'm writing the FF and the reset will row, and then after the 2 clock cycle I will on my reset, and then I'm calling my next task, read and check. So write data means it will only, this task will only do the writing operation, write operation. Okay, this task this task will do the read and check. Okay, so I'm here from this task I'm writing into RAM. Here in this task I'm reading and also I'm checking the outputs, whether I am getting the correct output. How I'm checking means it must be equal, data out and also expected value must be same. If both are same means the RAM design code is working fine. This is how I can test the this is how we can test the RAM code, like we can test the RAM design code. So I'll use the EDA playground to run this. Okay, same code here, so design code here and then test bench code here. So I just run this. Okay, so you can see the outputs here. So this is my test case, test 1. So reset is high, so reset is low. You can see here reset is low, so it means at the time all the input signal output signal must having the 0 value. So you can see here 0 0, we write in will also 0, address also 0, data in also 0, data out also I am having 0. Why? Because of this is my condition logic I was written in my design code. Okay, after 20 nanoseconds you can see in the design code also, you can see in the simulation after the 20 nanosecond only, you can see here after this 20 nanosecond only I am just on my reset condition. So I am giving the high value for reset condition, it means it will do execute. So here firstly I am doing the basic write and read operation. Okay, so this is my right reset is high, it means it can do work, and then write enable is low, it means I can read from the memory address. So the address is 00, and the data in is A0, and then data out is 00. So this means I'm just reading from the memory. So this is a return, so this is a return address 00, then the data is A0, so it will reflect in the next cycle. So data in is A0, and then data out is data out also A0. My address is 00. So 0 means 0x0 means I'm using here hexadecimal format. Okay, so this is my 0 address, my data in is A0. You can see here this output signal. So write enable is low means I can read from the memory. So address is 0, my 0th, in the 0th memory location I'm storing the A0 value, I'm getting the data out also same value A0 in the hexadecimal format. So here it means my test case is passed. Read this address, this is a value, expected also A0, so this is a pass condition. So it means the design code will work fine. And also come here, and also you can see here in my first location 0x1 means in my first location I am storing the value of A1, so data out also A1. So you can see here address also A1, data also A1, so expected data is also A1. So if both are, if the data out and also expected also matching, so the test case is passed. So you can see here this is how we can check the design code by using the test benches test cases. And also write to all the memory location. So here, so this is my test case 3. I'm going to write all the memory locations. So you can see here it will do incrementing. So 0 address here, this is my first address, this is my first address, this is my second address, third address, fourth address, fifth address, sixth address, seventh address, eighth address, ninth address, 10th address, 11th address, 12th address, 14th address, 15th address, 15th address. So each and every address I'm going to write. So writing data is nothing but this is my writing data. 65, 60, 75, 85 for 95 for my 9th location, 9th address, A5 for my 10th, A5 for my 10th address, B5 for my 11th address, C5 for my 12th address, D5 for my 13th address, E5 for my 14th address, F5 for my 15th address. So I'm just return all the data. I just return all the values to my memory. So in my test case 4, I'm going to read the data from the all memory location. So this is a memory location F5 in my 0th memory location. F5 in my 0th memory address. This is a first address 05, and then second address 5. So you can see here you can see the fail condition. So expected is 35, but data, so I am getting the output from the memory is 25, but exported it's a 35, so it is a fail condition. It's a failed condition. It means there is an issue in the design code. Okay, while reading the data from the memory, there's an issue, so we have to rectify that. Okay, so and then my next test case random access. Okay, random access. Here also I'm counting the test case and the test passes. So and finally you can see the output, number of test cases, number of total testers, number of failed testers. I'm doing totally 45 test cases. On that I'm having the 16 error. Okay, 16 fail condition, like failed test cases. So totally 45 test cases. On that 16 test cases are failed. So where I am failing means while reading from all the memory location, there is some issue. I want to rectify that. So this is the error in the RAM memory test bench code. Okay, so this is how we can test the design code by using the test bench very simply in the by using the display statements, and also we can see the waveform also. So and then this is how RAM code will work. I hope you guys are getting my point. So and then I will go to my FIFO. FIFO. So basically FIFO is mostly used for in the Verilog. In the design part we are mostly used for the synchronization purpose. Why? Because of mostly before FIFO memory or before FIFO works like a buffer. It will store the data sometime. So we'll see some basic architecture of the FIFO. So it is a write interface, read interface. So FIFO also one kind of memory, it having the memory, right? It having the memory location. So we need the address. So from the address we can read and write by using the enable signal, write data, read data from that, and then write enable. So write enable means I can write into memory. So I can write into FIFO memory. Read enable means I can read from the FIFO memory. So there is RAM and FIFO memory are both are same. So main purpose of FIFO is, so for example I'm going to paint. So assume like I'm assuming like you having the UART two devices, UART TX device. This is a UART TX device. So this is my UART RX device. Just a minute. This is a UART TX. Then this is a UART RX. Then this is a transmitter. This is a receiver device. So this is a receiver UART device. So both baud rate of the UART devices, transmitter device and then receiver device, both baud rate are different. So it means it having this device having the 9600 baud rate. Okay, so this UART device having the 115200. Okay, receiver baud, sorry, just a minute. So 115200. This is a baud rate for my receiver UART. This is a baud rate for my transmitter UART device. Okay, both are different. Okay, it means you can't make the communication between the transmitter to receiver. Why? Because of both baud rates are different. So at that time you can use the FIFO buffer. Okay, FIFO buffer is nothing but you can by using this. So you can use this FIFO buffer. So it's like a memory only. So memory means it will look like this. So it having memory cells. So just a minute. Okay. So this is assume like this is a FIFO memory. This is assume like this is a FIFO buffer. So UART will send the data to this FIFO buffer, and then from the FIFO buffer it will take the it will receive the data. So the main thing is the transmitter UART and then your receiver UART both are different, having the different baud rate. So if both are having different baud rate means you can't make the communication between the TX to RX. And that time you can use the FIFO buffer. So it's like a memory. FIFO like like a buffer. Buffer means it can store the data sometime. So for some clock cycle it can store the data, or it can store the data depends on our logic. So it's like a buffer. Okay, it will whatever giving the input, it will give the same output. Okay, this is a buffer explanation. So here in the FIFO buffer, it having some memory location. So from the transmitter device, based on this baud rate, it will writing into FIFO buffer, and then the receiver reward, it based on this baud rate, it will get the data from the FIFO buffer. It means, so we can make smooth communication between the TX RX TX RX of UART devices without same baud rate. So mostly FIFO buffer are used for synchronization between the different clock cycle devices or different baud rate devices. Okay, here both are different. Okay, so if you connect the TX RX directly with a different baud rate, means there is a chance to getting the unknown values or bugs. Why? Because of this transmitter device, this UART transmitter will send the data very slowly, but this UART receiver will get the data, it will always looking for data very fastly. Why? Because of this transmitter device having the low baud rate, but here the receiver device having the high baud rate. So 9600 is lower than 11500 baud rate. So it will send the 9600 data per second, but it can receive the 1,15,200 bits in per second. Okay, so it will receive the data very fastly. So if you send one, means it will send the, it will also, it is, if you send the 1 bit for the receiver, means so it will receive first bit, and then it will receive the second bit as a very quickly. So but both first bit and second bit are same, so there is a chance to have a error in the different baud rate communication in the UART protocol. On that time you can use the FIFO buffer. This is like a memory, so we can write into FIFO, and then so this transmitter will slowly write into buffer. This receiver will always getting data from the buffer. Okay, so firstly it will this device will send the data of start bit. Start bit means high, sorry, short bit means low. So low here, 0 will comes over here, and then so FIFO having, you know, the FIFO having functions of push and pop, push front, pop front, push back, pop back. So we can only add the elements from the top. So we can only add the elements from the top. So from the FIFO you can't access the memory location directly. You can add the memory, you can add the data from the top, and then you can get the data from the bottom. Okay, here we are putting the data into FIFO buffer. From the back side, from the last memory location of FIFO, we are getting the data. Firstly it will store here, and then at the next increment it will store first bit here, second bit here, and then after the one clock cycle it will store first bit here, and then second bit here, third bit here. So it will always increment the memory locations of the FIFO buffer. Okay, this is how the FIFO are used in real time scenarios to make the synchronization between the different clock devices, different clock frequency devices, different baud rate devices. Okay, so and then I hope you guys are getting my point. So if you guys any doubt, means you can ask now. So good evening Bharat Rajin, thank you for joining. So I think this is for today. If you guys any doubt, means you can ask now regarding the FIFO and RAM. So you can fill the attendance. You can fill the attendance in chat box. 16 day 16. So I think can I wind up the class? So if you guys any doubt, means you can ask now. If you don't have any doubt, means I can wind up the class. So FIFO architecture, just a minute. So this is a simple architecture of FIFO. Okay, this is a design. So this is a block diagram of my coding logic. So based on this only I am going to write the Verilog SystemVerilog code. So I will write this SystemVerilog code tomorrow session. So I will run the FIFO code tomorrow session. Today we are seeing RAM and FIFO memory, FIFO buffer. So I will write this FIFO buffer code tomorrow session. So it will look like this only. So like a FIFO buffer means you can store the data. So the main purpose of FIFO buffer is it will by using the FIFO buffer you can make a synchronization between the two different or multi different clock frequency devices and also two different UART baud rate devices. So to make the synchronization between the two devices, if you want to make the synchronization means you can use this FIFO buffer. So industry people, so for example, so assume like you having SoC, it having a lot of components, different clock frequency. CPU will work one clock frequency, and then GPU will work one clock frequency inside the chip SoC, system on chip. So and then direct memory access will work at some clock frequency. So all the components have work different frequency, but we have to make synchronization. So how we can means by using this kind of techniques. This is one kind of technique, like by using of FIFO buffer is one kind of technique to make the synchronization in the chip level. Okay, so this is for today. Thank you guys, thank you for listening. We'll see tomorrow with next topic. So I hope this session is helpful for you. So and then thank you guys, thank you for listening. We'll see tomorrow.